Welcome to Lecture 18 in our lecture series on stochastic processes. Today we will deliver the single, probably most involved result of this lecture series in this semester, which will state that a continuous martingale, in this case a continuous bounded martingale, has a unique and distinctive process of quadratic variation, which can be constructed by finite sums, by the limit of finite sums of quadratic increments, and which serves as the unique compensator for the square of the martingale, which in general is not a martingale any longer, but only a sub-martingale. And we will see that the quadratic variation process is uniquely determined as the only process of bounded variation, which turns this square of a martingale into a martingale upon subtraction. We have seen in the previous lecture that we would like to have the concept of a stochastic integral, for instance, with respect to Brownian motion, or with respect probably to more general martingales in continuous time. And we have seen that the most important example of Brownian motion, for instance, does not even have trajectories of bounded variations. That's why, for instance, the Stochastic integral concept will not be sufficient for the definition of a stochastic integral. And what will save us is the fact that continuous martingales have this distinctive process, which is the quadratic variation process, which we shall introduce with the theorem that I shall present to you now, and which will be the exclusive content of today's lecture, including, of course, its pretty involved proof. So the statement is as follows: let M be a bounded martingale with almost sure continuous paths. In the future we shall denote a process which has almost surely continuous paths, just a continuous process. Then there exists a unique continuous increasing process, which we shall denote in this bracket notation. Sometimes it's also just called the bracket process, which is a continuous increasing process, so the trajectories will have a non-decreasing behavior, which starts in zero, such that if we take the square of this martingale, the pointwise square of this martingale, and subtract this process of increasing trajectories, then this compensated process is again a martingale. That's one way to characterize this quadratic variation process as the unique process which is starting in zero, which is increasing in time, and which converts the process which is obtained from taking the square of the martingale back into a martingale upon subtraction, by subtracting this component. Note that in general, when we have a martingale and we take the pointwise square by Jensen's inequality, this will be in general only a sub-martingale. But if we subtract an increasing process from this, then there is a chance to obtain a martingale, and in fact this quadratic variation process does it. That alone would probably not yet be a full justification for calling this process the quadratic variation. In fact, this gives a characterization, but what is more intuitive and more instructive is that this process can be obtained, as one would probably expect from what we discussed before, by the sequence of square sums that the process that the process is exhibiting on finer and finer grids. So in other words, if we fix a certain grid delta, a grid of discrete number of time points in the time axis, and we consider the increments that the martingale is exhibiting on those time points that correspond to these grids, on these consecutive time points, and we take the square of these increments and sum this up, and we sum up these increments up to a maximal time when those increments should be evaluated, then this is a new process which depends on the parameter s as a time parameter. Of course, it depends on the chosen grid by which you do these discrete evaluations. Then this sequence of discrete approximations of what we would intuitively understand as the quadratic variation of the trajectories, then this sequence of discrete approximations of the quadratic variation does in fact converge to this quadratic variation process, for instance, in the following fashion, namely if we take the supremum over a bounded interval of time from 0 to t, namely, and if we ask what's the probability for a maximal deviation of this approximation from this target process by more than epsilon, then this probability for a deviation of more than epsilon of these two different processes with regards to the trajectories, then this difference, the probability for such a deviation, converges to 0 provided the mesh size or the maximal step size in this grid converges to 0. So that's a way how we can obtain this process, in fact, and in the end we will show this theorem in 2 steps. First we show that this limit exists, and then in the next step we will show that this limit process M does in fact satisfy these conditions, and then we will also show that the process M is in fact uniquely determined by these characterizing properties. However, the actual existence of such a process will be shown by showing that we have exactly this approximating sequence, which then ultimately leads to a constructible object, namely this M process. So let me read out the theorem to you once more. So let M be a bounded martingale with almost surely continuous paths, so just a continuous martingale, which is bounded. So there is some constant which bounds the total value which you can observe along these trajectories of the martingale. Then there exists a unique continuous, pathwise continuous, and increasing in time process, so the trajectories are almost surely non-decreasing, which we shall denote by this bracket notation, which starts in 0, such that the process M with the martingale squared, when we subtract this particular process, the bracket process, then this is again a martingale. And moreover, this bracket process can be obtained by taking the sum of the squares of the increments of this martingale on a finer and finer sequence of grid points, where this is understood as a process in the sense that we sum up these increment squares, or the squares of these increments, for a given time interval which extends from 0 to s. So as a function of s, this is again a process in the parameter s, and for all possible s values we have uniform in time approximation, or uniform in time convergence in probability of these approximate square processes towards the target process, this quadratic variation process, when the sequence of time grids on which we do this discrete approximation converges. The step size of the sequence of time grids converges to 0. That's the statement. So on the one hand, it's a characterization of this process, and the second statement, which is embedded, is that this process actually exists. As I said, this is the main theorem. It's the concept of quadratic variation, which is the cornerstone or the keystone in the construction of the stochastic integral, as you will see in the next lecture. And the proof is pretty involved, as you will see now. So we start with showing the existence of such a process, or to be more precise, we show that this sequence of discrete approximations of sum of square process, that this sequence has in fact a limit, and that will be the most complicated part of the argument of today. So assume we have a given time grid delta of innumerable time points which are ordered, and then we can have as a first important observation that if we take the square of the martingale and we subtract from this time discrete, or this discretized approximation of the quadratic variation along or with respect to a given grid, then this is already a martingale. That's the first important claim. Okay, so how can we see this? In fact, it's not so complicated to see this. The important observation is the following equality, which I sometimes call the Pythagorean theorem for martingales or something, but it's probably not quite a very good name for that. So namely, if I consider the martingale at two different time points, I take the square of this increment and I take the conditional expectation of this given the sigma field at time s, where I assume that s is less or equal to t, then I can just expand the square and note the following. So in this, after I do expansion of the square, the first term I leave unchanged. But in the second term, for instance, I see that I have a process of the mixed term in this square expansion. It involves an s and a t evaluation of the martingale, where the s evaluation is measurable with respect to the sigma field of s. So if I do this conditional expectation, only the mt is subject to the conditional expectation, which by martingale properties of course ms. So this, after an intermediate step, I can replace the mt ms, the mixed point expression, just by ms squared, because the mt alone is replaced by ms, and then it's put together again into the one expression. And this hits this ms squared, so in total I get an mt minus ms squared. So what you see here in this line here, in this little line, is basically already this martingale property, which is in this first claim. Namely, on the left-hand side of this equality, you have the increment square. Correction, you have the square of an increment on this macroscopic time interval. On the right-hand side, you have the martingale square, which you evaluate at different time points. And if you reorganize this equality, you have exactly already this claim of the martingale in a nutshell, which tells you that if you take mt squared and tt, and take conditional expectation to fs, then you get ms squared minus this increment term at time s. Now, of course, you can elaborate on this a little more in order to get the full statement, and I give a few hints towards this. So suppose for a moment that you have a time point t, which lies in between two grid points, tj and tj plus 1. And then I want to convince myself of the fact that this martingale property is correct if you project, for instance, down to the next lower grid point, tj, when starting from t. Okay, so I would like to convince myself that the required equality for a martingale holds true in this particular case. So I take the suspected martingale at time t, and I take its conditional expectation to this smaller time point tj. Okay, in order to do this, I recall this Pythagorean theorem, if you like, for martingale squares, which I insert at this level by adding and subtracting the mtj squared part, and I insert 0 by adding and subtracting the approximate quadratic variation at time point tj. And here's a misprint already, so there was this tj which was standing here. So that's a t here, in fact. So I add a 0 by adding and subtracting this approximate quadratic variation along the grid delta at time tj. And of course I subtract the same term again in order to keep the same value. Since this approximate quadratic variation at time tj is measurable with respect to the sigma field at time tj, I can insert or subtract this term inside or outside the conditional expectation just as I like. Okay, so I have, in this step, I have done basically nothing except adding and subtracting 0 by putting in those terms. And what I see already here is that by the Pythagorean theorem, this increment square, or this difference of squares, then by the previous observation is just the square of the corresponding difference when I evaluate this inside the conditional expectation. And this is exactly the term that is subtracted by the difference of these two sums of increments. So the only term that's changing in this sum of squares and this sum of squares is exactly the term which is obtained from here, which I can rewrite as a square of an increment due to this previously discussed Pythagorean theorem. So this shows at least that if I make this small step from a certain time point t to the next grid point to the left, then this desired martingale equality is correct. And in a kind of similar fashion, I can also convince myself that, if you like, this projection property from the closest by grid point from above is also correct. Namely, if I have another point of evaluation S, and I want to compare to this suspected martingale at the next upper grid point, I want to evaluate this suspected martingale and take its conditional expectation to the time point S. Then I can do a similar thing. I add and subtract a 0, which gives me, again by this kind of Pythagorean theorem, inside the conditional expectation, this increment squared. And by adding and subtracting this term of approximate quadratic variation at time S, this term appears inside also the conditional expectation. And then I look at the difference of these two sums of squares of increments, and I see that they differ only by one term, which is the step from the next lower grid point below the level S, either to the level S, which is the term which appears in this sum, or it's the corresponding increment squared from the same lower left time point tk, but now to the next upper time point tk plus 1. So these two terms, which are in fact sums of increments, they are different only in their respective last summand, and therefore in the difference is just the difference of these last two summands. Now this minus term here can of course be written as a sum, if you like, in a telescopic fashion, as the step from tk to s and then from s to tk plus 1. So this here can also be written, this bracket, the last bracket here, of course, I can also write as an mtk plus 1 minus ms plus ms minus mtk. So I'm just inserting a 0 again. And this comes with a square. So if I expand this square with respect to these two summands, I see that I cancel exactly, due to the minus sign, these two summands, and what remains is the mixed term, where at the beginning of, nevertheless, I should keep in mind that I had this term, two terms outside the conditional expectation, which are those that I want to see in the end. So they, of course, will be carried on. And so what remains from the conditional expectation is just the conditional expectation of the mixed term, which I've obtained by expanding the square here. Now, this mixed term, I have a factor which is ms minus mtk, which is because tk is below s, is measurable with respect to the sigma field fs, and it remains then, after I take this measurable factor out, just the conditional expectation of this increment of the martingale, which is a 0. So I see that also this expectation from this projection property, if you like, or condition expectation preservation property for the martingale is correct when I project from a grid point to an arbitrary time point which is below. And finally, it's a simple exercise to convince yourself that the projection or the martingale property is correct when you just consider just projections in between grid points from this grid point delta. I leave that as an exercise, and this in total, these three little computations in total tell you that from wherever you want to do the condition expectation to some other time point, might it be a grid point or not, you will get exactly this martingale property for this combined term. So let me say it again. We have just tried to convince ourselves that whatever the grid is, if we take the martingale, square it, and subtract this approximate quadratic variation which corresponds to that chosen grid, then this difference is a martingale, regardless the particular choice of the grid. That's a very important observation here. And you might wonder whether this would not already give the required quadratic variation process, because we have found a compensator after all, but it's not quite yet the compensator we are looking for, because this process as a process in time is not necessarily monotone. So it is of course monotone if you restrict this evaluation on time points which lie in the grid, because then you have this discrete increase of steps. But in between two steps, ti and t plus I plus 1, what you have in this sum is the last discrete increment squared, and then you just fill up the remaining trajectory by this continuous increments. And there is no increment squares, and there is no need at all to see that this number is anyway for a fixed ti, that an individual summand, if you like, when t, this continuous parameter, ranges between two of those grid points, why that should be a monotone quantity. So therefore this process for finite or for discrete grid delta, this process as a process in t is not yet a monotone process. Okay, ultimately the constructive statement of the theorem says that we have a limit if we take a sequence of grids of which the maximal step size converges to 0. And in order to show that there is a sequence and that there is a limit, we can compare two of such approximate quadratic variation processes. And if we have two different grids, delta and delta prime, we take the difference of the corresponding approximate quadratic variation processes. And our aim now is to show that this, in some way, is a converging sequence. This is a null sequence or a Cauchy sequence in some way, provided that the grid delta and delta prime have maximal step sizes converging to 0. For the subsequent discussion, we will also introduce short notation for the grid, which is obtained by taking the union of all the grid points of two different grids. So delta prime will be just the collection of all grid points which are in the union of the two different grids. Okay, so we want to make some statement, or we want to show that this xt process is a process which converges to 0. Recall that t delta, if we subtract the m squared process, is a martingale, and so for t delta prime, if we take the subtract the m squared process, is a martingale. So therefore this minus of these two t processes is this difference of two martingales, and therefore it is again a martingale. So the xt process is again a martingale. And we will show now that this xt process is converging to 0 by basically considering its square again. So we have a martingale. Again, we can take the square of this martingale. And if we have any other grid, for instance, the union of the two previous grids, and take the approximate quadratic variation of the x process and subtract that, we get again a martingale. So here, in fact, what we do is we take an approximate quadratic variation, we take its difference of two approximate quadratic variations, we identify this as a martingale, and that approximate of the difference of approximate quadratic variations, we again take the approximate quadratic variation, but now on the union of the two constituent grids. That's, if you like, a two-level type of quadratic variation of construction that we are currently considering. So ultimately our goal is to show that this x process is somehow convergent to zero or is close to zero if delta and delta prime have very little step size, maximal step size. So we fix a maximal time L, which is greater to naught. So since we have used the symbol t already for this quadratic variation, for this approximate quadratic variation, we choose another symbol for terminal time until which we want to consider the object at the moment. And we would like to show that this x squared process, or the x process, is a zero process, so why not try to show that x squared, that's x in L2 norm, converges to zero when we evaluate this x process at a certain maximal time point, capital L. Now, since this x squared minus t stuff is a martingale, which by construction starts in zero, this expectation is the same as if we take the expectation of this TL process, of this double or twofold quadratic variation or iterated quadratic variation process at time L. Right? So this process here is a martingale, which has zero expectation because it's a martingale starting at zero. So therefore, at any point L, this is a zero, an expectation, and so I can just split this zero and write one of the two parts on the left and the other on the right-hand side, which gives me this equality. And let me say it again, I would like to show that this x squared or so is zero. In fact, our aim is to show that this is true, that this goes to zero. So if that's true, since xl is the difference of TL and TL prime, it just says that TL goes to TL, or TL minus TL prime is a zero sequence in L2 space, which will then ultimately help us to conclude that there must be some limit in L2, so that this is a Cauchy sequence in the L2 topology when delta and delta prime converge to a continuum in the sense that their step size, maximal step size, converge to zero. Okay, now recall that x process is a difference of two approximate quadratic variation processes. So the TL delta delta prime is a TL of a sum of two. And if we take the approximate quadratic variation of two processes, of the sum of two processes, what we do in each of these summands is we take an a plus b, which is the sum of the one guy, and subtract an a prime plus b prime, which is the sum of the other two time points. But by a simple Cauchy-Schwarz inequality, if you like, this is less or equal than 2a minus a prime squared plus b minus b prime squared. It's just a simple inequality which comes from, I don't know, Cauchy-Schwarz or something, or just Young inequality. And we can apply this to each of these squares which appear here in this TL construction in order to convince ourselves that this twofold quadratic variation process of the sum is bounded from above by twice times the twofold quadratic variation process of either of the two. So you take this secondary quadratic variation with respect to the grid delta delta prime of the one component t delta, and we take the same secondary quadratic variation process on the same grid, but now apply it to the second summoned or second simple approximate quadratic variation process. And so in order to show that this is that the initial XL squared converges to 0 in expectation, it's enough. It will suffice to show that for one of the two that they converge to 0 in expectation. And I'm just recognizing that this square here in my presentation is superfluous, so it will be enough to show that either of the two, in fact both, converge to 0 in expectation, because we have this bound here on the right hand side, which is a pointwise bound. So if each of those two guys on the right hand side converges to 0 in expectation, then so does this term here, which is the quantity of which we want to show converges to 0 in expectation. Okay, so by the symmetric role that the T delta and T delta prime play, it will be enough, for instance, to take the example when we deal with the T delta. So we want to show now that in expectation T delta delta prime converges to 0 when delta delta prime converges to 0. Okay, delta delta prime is the union of the two grids, which is obtained from delta and delta prime. And suppose we have one, so L again is our maximal time to which we want to consider it. Suppose we have a grid point of the finer grid, which is below the level L, and let's take TL, let this denote the maximal grid point from the inner grid, from the coarser grid, which is still below the level SK. Then there is a next grid point which belongs to the finer grid SK plus 1, and since there are just many more, this finer grid point is still below the next grid point from the coarser grid, or at worst it is just a point from the coarser grid, it's just the next point from the coarser grid. So therefore trivially we have this inequality, which means that the next finer grid point must be still below the next grid point of the coarser level, or it must be exactly the next grid point on the coarser level, which is the case when the next grid point in the union is exactly taken from the coarser level already. And for simplicity, let us now write just a T delta whenever we actually deal with the T delta M. And now we want basically to obtain some estimate on this approximate secondary quadratic variation process, which is obtained by taking the inner process, which is the T delta process, evaluating that on such two subsequent fine grid points, and say something smart about that. Okay, so let's take the first order quadratic approximation process and evaluate this on two finer grid points of the finer grid. Then, since both of these grid points are still below or equal the next first order grid, the difference between those approximate quadratic variations on the first level will be at most a difference in the last summand of this first order quadratic variation expression, which will be these interpolations in between two first order grid points. So in other words, we have only this, in fact, let me say it again, this is a sum of discrete increment squares on the first order grid, but only when this SK guy is taken exactly from the first order grid. But if it's not taken exactly from the first order grid, then we have to evaluate, we have the last summand in this sum, which is an interpolation, if you like, between two first-order grid points. And this is exactly this interpolation, which appears in the last summand of this, in fact, sum of several squares of increments. And the same is correct for this evaluation of this approximate quadratic variation. And since both of these guys are still less or equal to a macroscopic, if you like, in this case, grid point, it's the same base point TL to which both relate in this interpolation between two macroscopic grid points. So therefore, these two sums of increment squares, which we take to a difference here, they each differ only from one another in their respective last summand, which then effectively is the difference of the two expressions. And by the third binomial formula, this difference of squares is the product of the sum and the difference, which is written like here. So we obtain that we have as a first factor the difference of the M process on these two fine grid points on the one factor, and then the second factor is the sum of the martingale on the two fine neighboring grid points minus twice the martingale evaluated on the next grid point to the left of SK, which still lies in the coarser grid. And it will be important to keep this in mind, that all these points of which are related here, they are all these, so the points which are appearing here, the time points SK, SK plus 1 and TL, by definition, they are no more than, say, 2 times the maximal grid size of both of the grid delta and delta prime away from each other by construction, because TL is the next most coarse grid point to SK, which by definition can be no further away from SK than just the grid's maximal step size of the coarse grid delta and so forth. Okay. So let us keep this in mind. And so this means in particular what? That the the difference of these two evaluations of the T delta process on these two fine grid points, when we take that to the square, of course, is bounded from above by the maximum of these second factor along all these possible SK and TK associated TL points times the difference squared of the M process on the fine grid points SK plus 1 and SK. This is just a straightforward consequence of the previous identity. So this means that if we evaluate the secondary approximate quadratic variation of the first level approximate quadratic variation, which is a sum, after all, of all these increment terms squared, then this is bounded from above by the supremum of all these binomial terms, this error terms squared, because it's the sum of the squares, times the squares of these guys here. But these guys here, they are familiar. They are corresponding to the first order quadratic variation of the M process when we work with the joint grid or the fine grid delta, delta prime. So this inequality here then is a straightforward consequence of the previous definition by just taking a sum with respect to all these neighboring pairs SK plus 1 and SK. Now recall that we wanted to assume that M is a continuous martingale, so the trajectories of M are continuous. And we evaluate all this, or we discuss all this on the compact time interval from 0 to L. And so we know that for almost all trajectory, by uniform continuity, if these mesh sizes of the two grids converge to zero, for almost all trajectory, this is a zero sequence, just by uniform continuity of a continuous function on a compact interval. And also we know by boundedness, since we know that there is a certain constant which bounds all these m values, this is a uniformly bounded sequence of functions which converge almost surely to the zero function. So therefore, the expectation of all this supremum, for instance, if we take it to the fourth order, that would converge to zero by dominated convergence. Okay, recall that we wanted to show that in expectation the left-hand side converges to zero, and we have on the right-hand side a product of two terms, of the one of which we can control nicely, or which we can say it's a zero sequence even in expectation, even in inappropriate power. And what remains to show, for instance, is that if that would be just perfect for the application or for the conclusion as follows, namely, if we want to show that this quantity in expectation converges to zero by the pointwise upper bound, we can bound this expectation by this product here on the right hand side of these random quantities. And then we could apply a Cauchy-Schwarz with a square, which would give us the square, the fourth power of the supremum term, raised to the power 1/2 or square root of that, and would have the t guy, the secondary correction, the first order quadratic variation on the refined grid of the m process, taken to the power squared to the second power square root of that. That would be just Cauchy-Schwarz here. And we know that the first factor of these two expectations converges to zero by just what we had said. It's uniform continuity, so it's a zero sequence pointwise. And we have a dominating number C, if that's the total bound or the uniform bound on the realization of the m process. So that's a perfect zero sequence. And what remains in order to conclude this argument is to show that this collection of expectations of this first order approximate quadratic variation in fact in the power 2 is uniformly bounded when delta and delta prime tend to zero, because then we have an upper bound which is uniform and the convergence statement would be established. So therefore it remains to show that this sequence of expectations on the right hand side, the right factor, is uniformly bounded. Okay, and we will show that for a general partition delta tilde, so in particular for a partition which is obtained by merging two other partitions. So choose any partition delta tilde, and we want to show that the expectation of this first order quadratic variation raised to the power 2 is uniformly bounded. Okay, so we write down the square of the first order, or the square of this approximate quadratic variation. The approximate quadratic variation is the sum of these increments squared. If we square this, we in fact get a double sum, where one summation parameter is L and the other is K, or TL and TK. Again, it's a little misprint. Okay, so that's the double sum which we get. The double sum, of course, contains a diagonal part, which I separate, and it contains twice the same off-diagonal part, which is the summation with respect to K, and then we get the summation with respect to all L, which are strictly greater or equal to K, of these two components of factors, which in this case each are squares of increments. Now, if I fix, okay, so now I'm going to continue to work with this decomposition. I keep the diagonal part as such, and as for the off-diagonal part, if I keep the exterior parameter k fixed for a moment and consider the summation with respect to the L parameter, what I see here is that I do consider again, so again let me say it again, so here I'm considering only this sum with respect to the L parameter of these squares, and I see that this is again the sum of squares which appears in the first order approximation of the quadratic variation. But here I sum over all indices which are above a certain starting index, which means that the sum of these squares is the remainder of a difference of two finite sums, where one of these two sums is taken up to the level L and the other is taken up to the level L inf tk plus 1. So here, let me say it again, suppose you take this factor out, and you have the sum with respect to k. What you see here is that you sum up these increment squares with respect to the L parameter, TL parameters, for all L greater or equal to k plus 1, which means that the first increment that you consider here is the increment from level TL plus 1, tk plus 1 to inf L to tk plus 2 inf L, and then you sum all remaining sums of these increments squared, which in other words says that you have the full sum of increment squares minus a first part of sums of increment squares, which is the first part what you get if you sum up to tk plus 1. Okay, hence, if I take the expected value of this first order approximation of the quadratic variation of the M process, and I take the square, that's the quantity of which I want to show that it is uniformly bounded, independent of the particular choice of the delta tilde grid. Then I have these two summons. One is this diagonal part, which contains the fourth order increments, or the increments in fourth order. And then I have this expectation over the off-diagonal summons. And each of these off-diagonal summons I shall denote by an eta k. Now let's consider the expectation of the eta k. Okay, before I take the expectation by this projective property of condition expectation, I can first take the condition expectation of each eta k when conditioned to the sigma field belonging to the moment of time tk plus 1. Now, if I have a look at this eta k guy, well, eta k is if you write it like this, if you condition, as for the condition expectation of this to the sigma field tk plus 1, you see that this is measurable with respect to the filtration, and this one as well, so the square it is. So therefore that increment squared can be taken in front of this condition expectation, and what remains is this difference of these approximations of quadratic variation. And then we already have seen that this is a compensator, not necessarily an increasing, but is a compensator for the ML process squared. So therefore the expectation of these differences is the same as if I take the expectation of the difference of the martingale at these two respective martingale squared at these respective times. But again, by the Pythagorean theorem, if you like, for these martingales, I can replace this by the difference of the martingale on these two different time points raised to the power 2. So again, this is there's two arguments here which I combine in one. And first of all, that TL minus ML squared is a martingale, or TL squared minus ML squared, that this in expectation is 0, and also in condition expectation, if you like. And then I used, so I could replace this TL by this ML squared and ML inf tk plus 1 squared. And then I used, as I just said, this relation that I had used already before, that in expectation or even in conditional expectation, that the difference of a martingale squared is the same as the square of the difference of the martingale. And then I can unwind the conditional expectation again and forget it effectively, and I obtain simply for this off-diagonal part that this is mtk plus 1 inf L minus mtk minus L, inf L, that was the factor which was there before, times the martingale at time L minus the martingale at time L inf tk plus 1 in the powers 2. Now I can, for instance, recall that the martingale M was assumed to be bounded by a universal constant C, so I have the difference squared of two numbers which are each no bigger than C, so that difference is no bigger than 2 times C squared, for instance, as a factor, which I take out of the expected value, and I'm left with this expectation of tk inf plus 1 inf L minus inf mtk inf L. This was the expectation of the eta k. So I had just given an upper bound for the expectation of this eta k, but inside the actual quantity of which I want to compute an upper bound for, I have the sum over all these k values. So if I take the sum of all these k values and insert this into the right hand side, I get a 4. Why do I get the 4? Let me see it again, because the factor 2 in front. So all this adds up to an expectation on the right hand side, again by 4c squared e to the tl of delta tilde of m. That's the component of the off-diagonal part of these expectation of the quadratic variation, the discrete approximation of the quadratic variation squared. And then I'm still having the diagonal part. The diagonal part involves these increments raised to the power 4, but by the same argument I just get rid of 2 powers by estimating again by 2 times c squared in each of these factors. So that's here. And what remains is just, again, the first order approximation, or just a standard discrete approximation of the quadratic variation of the M process. So in total I get, if I counted powers and constants right, an upper bound which is 6 times c squared, where again c is the constant which gives the uniform bound by assumption on the realizations of the martingale alone, times the expected value of the discrete approximation of the M process at terminal time. But again, by our Martingale property, this expectation of the approximate quadratic variation is the same as the expectation of the Martingale squared at terminal time. It's again this Martingale property of the compensator, or of the Martingale property of the square of the Martingale minus this particular compensator, which is not necessarily monotone in trajectories. But again, since I know that M is uniformly bounded by a constant c, but the same constant, this whole thing is bounded from above by c squared. So in total, I get an upper bound for this expectation by 6 times c to the power 4, which is finite and does not depend on the chosen grid delta tilde. Okay, so this was all the pain, and now we can just collect. After all this work, we have seen that for a sequence of, or for 2 grids, delta and delta prime, or for a sequence of grids, delta, delta prime, whose maximal mesh size converges to 0, we have that these T processes evaluated at capital time L, for instance, they converge to 0 in L2, but this is a difference of martingales at terminal time. And we have a maximal inequality for martingales, which is the dupe maximal inequality, for instance, for the submartingale, which is obtained by taking the square. And when I'm talking about the maximum inequality for martingales, I should probably make a statement here that I didn't discuss, that all the inequalities and statements that we derived previously for time discrete martingales, they carry over to the continuous case just by approximation with respect to rational time points, for instance, and using the continuity. So all these statements about maximum inequality, convergence, closability of martingales, all this is correct. All this carries over verbatim to the case of martingales in continuous time, but just using the fact that it's all true for, say, rational time points, and then concluding the rest by continuity of the paths. Hence, we have Dub's maximal inequality at our disposal, which allows us to conclude that these pathwise suprema of these difference of martingales, which is again a martingale, also converges to zero. Now, pathwise suprema convergence is very good because each of these STS processes are continuous. And so therefore, if we have for almost all omega, we have a limit, which is a limit in the uniform topology of continuous paths. So therefore, there is a continuous process, which therefore shall be called MM. We could have given it another name, but there is, we choose to use this name for various reasons, which we will work with in the future. So there is some process, which is a continuous process with continuous trajectories, such that we have the corresponding type of convergence, namely we have locally in time uniform convergence of the trajectories in expectation, and by Chebyshev inequality also in probability, if you want, if delta tends to zero. And moreover, by a standard argument that we can all do, this limit process will be unique. It will not depend on the particular choice of sequence of grids, because if you have two different grids, then you can form a joint union sequence of grids, and it will have the same limit. And this kind of argument shows you that the limit will be unique and not depend on the particular choice of the delta sequence. Moreover, I claim now that this process is monotone. Why so? Well, by just construction, this approximate quadratic variation process is increasing whenever you evaluate this approximate quadratic variation process on time points which belong to the grid, because then you have discrete increments which are taken squared, which are taken into a sum. So whenever you go a next step, you have a discrete summand which is added, and so therefore naturally this process as a process in S is monotonely non-decreasing when you restrict to grid points. Now we can choose for the argument and for the analysis of the limiting trajectories a sequence of grids which are refinements of one another. So it's an increasing sequence. And then we can conclude just by the uniform convergence of the trajectories that this limit trajectory will be monotone whenever we compare time points which belong to this union of grids, which is a dense subset. And by continuity of the trajectories, we have, in fact, that this M process is really a monotone process for all trajectories. So therefore, this limiting process, in fact, will be a monotone process. And that will be a consequence of the fact that all these approximating processes are monotone when we restrict to the corresponding sequence of grids. And finally, we also claim that this is a martingale if we subtract this bracket process. Why so? Well, we know that for all possible grids delta, we had shown that mt squared minus tt with that grid is a martingale, but the tt process converges in L2, for instance, against this mm process, the bracket process. So therefore, it's a simple consequence of norm convergence in L2 or so, that also mt minus the bracket process must be a martingale, just by continuity of conditional expectation with respect to L2 convergence, if you like. So therefore, ultimately, we have convinced ourselves that there is this process. there is a process which can be approximated in the given sense by the sequence of approximate quadratic variation processes. The limit process will be unique, independent of the approximation. It will be a process which is continuous in time. It starts in zero and it's non-decreasing. And if we take it as a compensator in order to subtract that from the square of the martingale, then it gives back a martingale. What remains to be shown is the uniqueness statement. Okay, we claim that the uniqueness follows from the following properties. So let me say it again. We have a process which is here denoted as the bracket process, which has the property that if we take the square of the martingale and subtract that, we get back a martingale. The process M has continuous paths. It starts in zero and it is monotone, pathwise monotone, increasing, which in particular implies that it's of bounded variation. And I claim that the uniqueness of this process M, that there's only one process which can do that, follows from the following lemma. Namely, if A is a continuous martingale, which starts in zero, and which is pathwise of bounded variation, then A must necessarily be the zero process. Okay, to show that, we convert the problem first in such a way that we deal with a bounded process, namely let tau be the following stopping time, which is the first time that the process A that we deal with in absolute value exceeds a certain threshold k. Then the corresponding stopped process is obviously a process which never exceeds the level k in absolute values, so therefore it's bounded. And by optional stopping, it's still a continuous martingale. And it's of bounded variation because we haven't changed the paths until stopping, but obviously if you stop a continuous path, then even after stopping, it is even of less variation than before the stopping. So it's certainly still a bounded variation path, and it also starts in zero. And so in particular, we can apply this idea of a quadratic variation that we have just demonstrated. We have at least one process, which is a nice compensator. So in particular, if we take the difference of the expectations of this process at two different times by the martingale property of the compensated process, this difference of expectations squared is the same as the quadratic variation of the process, of the stop process at time L. But we have already seen in the context of Brownian motion that if we have a process which has finite variation, which is here the case, then it has quadratic variation 0. So therefore this, if it's continuous, and so therefore this quadratic variation in fact is a zero process. And in particular, we find that the expectation of the A process stopped at time L raised to the power 2 is the same as the A process at time 0 raised to the power 2, which is, since the process was starting in 0, 0. So hence we find that the stop process at any time L must be 0. And obviously this is good, so we can send the threshold k now to infinity in order to convince ourselves that at any time the unstopped process is also the zero process. At any time, which is the claim. So therefore there's only one process of bounded variation with continuous paths which starts at 0, which is then having additionally this compensation, the compensated property. And we have found such a process by construction for a bounded martingale, which is this bracket process. So therefore the bracket process is uniquely determined and uniquely characterized by this property, whose existence, let me say it again, we have shown by a completely different argument, by this sequence of approximate quadratic variation processes. Okay, so this concludes today's lecture. It was devoted entirely to this existence of a quadratic variation process and its properties for a bounded continuous martingale. And then the next lecture we will extend this to not necessarily bounded martingales, and we will hopefully show already next lecture that this is the key step in order to define the stochastic integral, where a continuous martingale is the integrator